behavior. If you graph this, you're going to see that you have a vertical asymptote in here at -1, and it's sending your graphs off in a different direction. Like it's a weird shape too, like one goes this way, the other goes this way. So there's a slant asymptote that falls in here that models this end behavior. End behavior is looking for, Alright, so now we're looking for an end behavior. What is going on here? Alright. Let's try it again. Okay. Alright. End behavior says, and one of your rules for your asymptotes, your horizontal asymptote, we have a vertical asymptote because that's the guy in the denominator. But your horizontal asymptote says if the numerator, the exponent in the numerator compared to the exponent in the denominator, well, when the exponent in the numerator is one more than the degree in the denominator, you first do not have a horizontal asymptote, and secondly, you have a slant asymptote. So slant asymptote requires you to do synthetic division. So we're going to start with the synthetic division. We're going to pull out your coefficients, and you have to make sure you account for each one. -2, 5, -1. Okay? If we were missing one, we put a space holder in there. Then you're going to put your root right over here. This is a factor. So if we set this to 0, our root is -1. Not a root necessarily, but like as if it was set to 0. So now, bring this guy down. You're always multiplying to the right, add down. Multiply to the right, add down. So we multiply -2 times a positive, -1 times a -2. We get a +2, add down. -1 times a 7, -7, add down. Now, in your slant asymptote, it has to be a line. This guy is the x. So here's your line, right here. I don't need the remainder here. There's the equation of your line. Y is equal to -2x plus 7. That's the equation of your line. If you graph that function, let's take a minute. Let's just graph this function. All right, let's graph this, and then we're going to graph your slant asymptote right underneath it. And then I'm going to put your slant asymptote in here. It's going to be a line. If when we graph this, here's my graph, here's my asymptote, it's sending this at -1 in different directions. Certainly isn't my graph. There goes my graph. See your slant asymptote? The other guy's up there somewhere. But you see your slant asymptote, how it guides that end behavior? Your horizontal asymptote did that with a limit. Your slant asymptote does that when it curves down with your end behavior. Okay, now, another one that you had was when we had 2 of them. When we did this, we had to do a double divide. So we had to pull all of your coefficients plus the numerator part, but be careful. you have to account for each one. So there's a 1. That's 5. I'm missing a 4. I'm missing a 3. I have a 2. I have a 1. I have a 0. Remember we used to say 5, 4, 3, 2, 1, 0. Make sure they were all there. Now we have 3 terms on the bottom. The leading coefficient of the first one has to be a 1, which it is. So this is where your double one came in. We took out the 3 and the negative 5, a double one. And we did a double synthetic division. We'll walk through one of these. So I bring down a 1. You're still always multiplying to the right. 3 times 1 is what? 3. And I got a negative 5. Negative 5 times 1, negative 5 to the right. Stop and add this one down. Then we do it again. 3 times 3 to the right. Negative 5 times 3 to the right. Stop and add this one down. Remember doing this? 3 times 4 to the right. Negative 5 times 4 to the right. Stop and add this down. Okay. 3 times negative 5 to the right. Negative 5 times negative 5 to the right. Stop and add everything down. So this gives me negative 30 and this gives me 22. Now, real simple to figure out where you start. x5 over x2. What's my x going to have as an exponent? x5 over x2. X, whoops, gives me x cubed, right? This is my x cubed, my x squared, my x1, my x0. This is my remainder. So x squared plus 3x cubed plus 3x squared plus 4x minus 5. Then your remainder, negative 30x plus 22 over your denominator. Okay, remember doing these? You had to do a double one for this. And every time you do it, same process as the other one. You just have 2 things to multiply. Now, jump now, and more importantly, let's go down to number 15, I think it is. This guy. You need to find all your real zeros using synthetic division. How many zeros in this polynomial should you have? What tells me how many zeros you have? The highest exponent. So how many zeros should I have? 4. Now I can't factor this, I can't group this. So the best way to do this is put it in your calculator and look for your zeros. You need at least 2, because once you get to a square, you can factor it. But until we get to a square, we can't factor it. So let's break this down and see if we can locate at least 2 of them. So we put this in. Put it in your calculator too, so you know what you're looking for. Okay, oops. Mine's always a delay in here somehow. Okay. Yeah, I don't care where it turns. What I care about are those little zeros. And I probably can't even see too many of those in there. But I'm going to make my window kind of zoom in to that x-axis. I'm going to go -1 to +1. So I can zoom into my x-axis. There's one. There's another. There's another. and it kind of bounced off of that. Remember when it bounces off the x-axis? Anybody remember what it's called? Because I should have 4. I only see 3. 1, 2, 3. Double root. When it bounces off the x-axis, it's a double root. So now, I need to go to my table. I can clearly see that one. -6, 0. And I need to find at least one more. So in my positives, there was something there. And there's one. 1, 0. So I have 2 roots that I can use to start with. So we're going to start dividing this out. Do you want to start with the -6 or do you want to start with the 1? 1? Okay, 1 is out. Pull out all your coefficients. 4, 3, 2, 1, 0. We're going to divide. Regular division. Start with the 2 down here. Multiply to the right, add down. Multiply to the right, add down. 1 times 2, 2. Add down. 9. 1 times 9, 9. Add down. -17. 1 times -17, -17. Add down. 1 times 6, add down. This should be a 0 because you found a 0 there, no remainder. Now we're going to do it again. So don't move anything. Set it up again. Take your next root. Bring down 2. What's -6 times 2? -12 to the right. Add down. -6 times -3 to the right. Add down. -6 times 1, -6, and this again should come out to be a 0 because that was one of our roots. Now we went down 2 roots. So from x to the 4, we did that one. We did x to the 3. Now we're down to x squared. So this is 2x squared minus 3x plus 1. We've got to factor this and set this to 0. If we knew another one, we could again factor and then just at the end find the last root. But now we've got to factor this guy. Now, to see if this is factorable, what is 2 times 1? We'll do a times c. 2 times 1 is 2. So I have factors of 2, that gives me -3. -2, -1. So this is factorable. So we know there's only one way to factor a 2, one way to factor a 1, and both of them have to be negative. There's your factors. Set them equal to 0. So x is 1/2 and x is 1. There's your double root. We already had 1. See where it bounced off? Robert said that's called a double root. Bounced off. The other guy we could barely see because he was in between 0 and 1. We couldn't find him on our table. So we found 4 roots. You only have to write the double root once. If you want to write them in order, that's fine too. Probably a little bit better. Here's your roots. We could have started with the -6. Yeah, yes, and I think it was what year Rebecca yelled out one. I'll listen to that. It would be the same answer. And that's something that we might see. Better with the synthetic division? Okay, let's go back to the answers. And I don't know why, but my answer key came out so messed up. I was working on a formula sheet here. Okay, for this first one, all right, for this first one, this is a rational one. This is the one that has a fraction in it. And you have a series of steps you have to follow to get there. So the first thing we do is we factor. You always factor and reduce. Or graph, first of all, actually. Graph and get a sketch of this. So you can kind of see where your asymptote is. You can see where the end behaviors are going. You can follow your limit as x approaches infinity. You can see where your y is going to be 0. Ties into your limits, that's your horizontal asymptote. Factor, the guy you factored out, this is your point of discontinuity. That's your point of discontinuity. Reduce it, keep your reduced form, so that if I could plug in that point, it would be 318. If I looked at it in my calculator from both directions, it would approach 1/8. Okay? Then follow the whole steps. Whatever's left in the denominator is a vertical asymptote. And now you know, here's your vertical asymptote. X is equal to -5. Horizontal asymptote, you had 3 rules. Can you guys remember those 3 rules? Okay. If the degree in the numerator is less than the degree in the denominator, you have a y equals 0. If we did a limit, then it would, as x approached infinity, it would be 0. It's the same thing. So do you see where your end behaviors are going? Eventually, they're going to get real close to 0, but never touch it, right? Because that's where your asymptote is. So that's your horizontal asymptote and your limit as x approaches infinity. Okay? Your point of discontinuity, remember for your range and your domain, you have to take out your point of discontinuity. And obviously we can't use spot -5 because that's a vertical asymptote. And so here's your limit as x approaches infinity here, and as x approaches -infinity. Isn't it approaching your horizontal asymptote where y is 0? Okay. After you factor, when you reduce, the one that you take out is a point. What's left in here is an asymptote. So once you reduce your function, when you take that out, that's this little guy right here. That's the one we can make a removable point. It's just one little, when you graph this, you can't even see it on your graph, but when you look at your table, you can see that 3 says error. Okay, this guy, this is important, and I apologize for this. I don't know what happened to this writing. I think when I saved it, I don't know what it did to it, but some of my writing came out okay, and the rest, I don't know what happened. I must have hit something and written in another language or something. Now, we talked about this the other day, your domain restrictions. This has a radical under a denominator. You have to take this and set this greater than 0. And because this is a quadratic, we have to find your roots. So we have to say, okay, set this equal to 0. So I get 25 minus x, 25 plus x. So my roots are at plus or minus 25. Here's your number line. They can't be closed because they're in a denominator. They can't be 0. So they're open. You have 2 ways to do this. You could graph this original function. You could go in your table to the left of 25 and see if those y values are negative or positive. Or you could sketch this quadratic, and you might remember us doing this. This quadratic opens which way? Down. So my quadratic is looking like this. This is like my x-axis. This is where my negative y's are. This is where my positive y's are. This is where my negative y's are. Or find them in your table that way. I want positives. So I want, where x is positive, right in between here. So I want from negative 25, I can't use 25, to positive 25. Because doesn't that make sense to you? If I pick 25, that'll give me 625 minus 625. That gives me 0. If I pick 0, because doesn't 0 fall in between there? 0, I'll have the square root of 625. I can take the square root of 625. But if I come out to this above 25, if I did 26, that would be greater than 625. That would give me a negative under my radical. So you can kind of tell when you graph it. You can kind of tell when you set this up. The quadratic under the radical is the trickiest one. Okay, we did your end behaviors, right? We synthetically divided that. I'm at a loss today. I'm really at a loss. I can't do this. Go down. I can't even knock out of this. We're up and running again. So this range, how do I know this range? Well, I'm going to graph it first. I'm going to graph this. And I can tell what my domain restriction is. I can tell that x, if I set this equal to 0, when x is 1/2, this is not going to work. So this gives me an asymptote at x is 1/2. And I look to see where my horizontal asymptote is. My horizontal asymptote is, these x's are exactly the same. I pull this out right here. xy is now 1/2. So I can't use a y of 1/2 either. All they care about is my range or my y values. So I just can't use a y of 1/2. And it's just this one. I don't care about my x values, just my y. Kind of a long way to get there. Here's a good one. This makes you look at your horizontal asymptotes, your vertical asymptotes, your point of discontinuity. So the first thing you do is factor. Factor and reduce. What you reduce is a point of discontinuity. What you're left with, I can't even read this, over x minus 4. What you're left with, this is your vertical asymptote. Your horizontal asymptote is y equals 0. So I have a horizontal asymptote. Oops, no, I'm sorry. It's both the same. Your horizontal asymptote is y equals 1. Okay, because they're both the same. So we got this guy. A vertical asymptote? No, my asymptote is at x equals 4. So that one doesn't work. And then I go to, that's where my point, this is where your point of discontinuity. So my y-intercept is when x is equal to 0. So I'm going to get a 0, 0, 0, 6, 0, 0 over 8. And this reduces to 3 over 4. Good? You guys are good with this? All right. Can everybody find this one, relative max? Put it in your calc, do a max. Okay, that's kind of a nice little 2-point question there. Okay, here's another one. Again, factor it and reduce. The factor that comes out is your point of discontinuity. So when x is 7, it's your point of discontinuity. So therefore, it can't have no discontinuity. An infinite discontinuity, no. Point of discontinuity. Find all asymptotes and a point of discontinuity. So reduce it and sure. I know I don't know what happened to this writing here. You can't read this? Really? I can't either. Okay. Okay, so we factored the top are perfect squares. The bottom, trinomial. The one that we can remove, that we can get rid of, this is your point of discontinuity. So you start like this. When x is 7, I have a point of discontinuity. What is my y? Well, I take my reduced function, and now it's like your limits. I can plug this in, because I couldn't plug it in before until I reduced, so I could plug it in. This is where you did your limits, when x approached 7. So now we plug your 7 in. So we get 14 over 6. So if you want to reduce this down to 7 over 3, that's fine. So 7/7 is your point of discontinuity. What's left in your denominator is your vertical asymptote. That's not going to go away. That you're going to clearly see is going to change your graph. The point of discontinuity, when you look at your graph, you won't notice it because it's a point we can remove. A vertical asymptote we can't remove. So your vertical asymptote says take this and set this equal to 0. When x is 1, I have a vertical asymptote. Horizontal asymptote says my degree in my numerator is the same as my degree in the denominator, so y is their coefficients, the ratio. If I did a limit as x approached infinity, its value would be 1. It's going to approach a y of 1.
The 7 times 7 over 3
is the point of discontinuity.
How do you know if you don't have it?
Because if you can't reduce it out, you don't have a point of discontinuity. What I would do first, Justin, is always graph that. I think by graphing it, it makes a big difference. You can actually see when you graph it. Let's throw this in the graph. They say a picture is worth 1,000 words. It seriously is. It just makes you be able to see each one of these. My whole board has been acting up today. Okay, so let's graph this. Can you kind of see where this one's going off? Oh, let me zoom 6, sorry. Can you kind of see this one separating? You can't really tell at the 7 that it's not working right until you look at the table. When x is 7, error. Now if I got closer to my table, remember how we did this? We looked at your limits graphically. If we looked at your table, we could say, look, I could see it's going to approach the same number. That's a removable point. I bet you if we divide 7 divided by 3, we get 2.3333, right? That's our 7/3 right there. So we know where it's going to approach. But what we can't stop is this asymptote right here. We can't change this one. And we could see that your y is equal to 1 is your horizontal asymptote. Because your end behavior says, well, as x approaches infinity, y is going to approach 1. Does the infinity part make a little bit more sense now, your end behaviors and those kind of things? It's the same thing we've been doing, we just called it something different. What else do we have here? We did that, and I said, don't worry about that. Okay, here's another one. I have to describe all asymptotes. So the first thing that I do when I see this is I factor. I factor this, and it's a double factor here. And then the bottom, I factor. I say, do I have a common factor in the top and the bottom? This is my point of discontinuity. If I can remove this, it's removable. It's my point of discontinuity. What's my y value? Just reduce your fraction. What's left in your denominator is your vertical asymptote. Your horizontal asymptote says x is the same in the numerator and the denominator. Take the coefficients. So this gives me all your asymptotes. I didn't want a point of discontinuity, I just wanted the asymptotes. So I'm looking at this one, and I'm looking at this one. Negative x is equal to negative 2. So every time you see this, you're going to take your function and you're going to factor and reduce it. What's left in the denominator is a vertical asymptote. The horizontal asymptote is the ratio of your y's. The ratio of your coefficient of your exponents when they're the same. Okay, can you do this, guys? Find me your relative min, find me your relative max, and do those relatives. Remember to say relative versus absolute. This one we did together. And this guy okay? A decreasing. For decreasing, you're going to find your relative max. You're going to find your relative min. You're going to give me its x values, right? From the max to the min. Decreasing. I know it's very hard to read. I don't know what happened to this. How about this? Did you do this one? The equation of the polynomial? Let's do this one together. We didn't go over that one? Yes, we did. You didn't do that this year. I don't even know where this is coming from. Okay. Okay, let's do this together. Okay, now, if I, on the side here, if I gave this equation, and I factored this, and I had to find all the zeros. I work it that way, right? Now, I'm going to give you the zeros. You're going to work it backwards. So you're going to say x is equal to 2. Oh, this factor, set it equal to 0. Oh, I got a factor of this. These guys are conjugates. They're pairs. That means they came from a quadratic equation because I couldn't factor it. They followed this equation. Now, we have two formulas, and I will give you these also. Sum of the roots, negative b over a. Product of the roots, c over a. Easy as pie. Put it in your calculator with a plus. The I is above the decimal point. These are coming out. Your sum is going to be 6. We're going to let a equal 1. Therefore, what's b equal to? Negative 6. Good job. Now, we're going to pull this down and we're going to multiply. Let your calculator multiply. They're perfect squares. They're the first term and they're the last term. What's I squared? Anybody remember? Negative 1. So this becomes 9 plus 4, 13. C over A. Therefore, what's C? 13. So now, I've got my equation. I have this factor, and I got this quadratic that I had to use the quadratic formula on. And there's your function. And you can leave it in factored form.